Welcome viewers, in this video we will see the construction of a DC machine. Subscribe the channel for more electrical videos. The soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic, construction of a DC machine. The DC machine is a device which converts electrical energy into mechanical energy or mechanical energy into electrical energy. So while converting mechanical energy into electrical energy, it is called a DC generator. While converting electrical energy into mechanical energy, called a DC motor. So the same machine can be used as either a generator or motor. So there is no difference in the construction. The same machine is used for generator as well as a motor. So that it is called a DC machine. So the construction will always deal with the DC machine. So that machine can be act as either generator or motor. So the DC machine mainly having two main parts are available. The stationary part and rotating part. The stationary part is nothing but producing the magnetic flux. The stationary part is nothing but the coils are available, windings are available, so that will produce the magnetic flux. The rotating part is nothing but a armature. There also the coils are available. So the conversion of electrical energy to mechanical energy or mechanical energy to electrical energy will be takes place in the armature. Right. So we have the detailed diagram available at the time, we can easily understand. So the mainly we have stationary part, that is the coil, it will produce the magnetic flux. Rotating part called the armature, the conversion takes place in the armature. Now we'll go to the detailed diagram. So this is the stationary part. This one is the stationary part called a yoke or frame. Here the coils are available. It's called a field windings. The stationary part, the coil what is available is called a field winding. So the center what we have is the armature, rotating part. So there also coils are available. Right. So this is the stationary part and this one rotating part. So in the stationary part we will see first the yoke or frame is available, outer cover holding all these windings and armature, the outer frame is available. See, this is the pole core. Pole core is nothing but where we are going to place the coils. Here the pole core, this one pole shoe. So this dotted line is nothing but a coils, field coils. Right. So this dotted lines, this shaded portion is the field winding. So the field winding is placed in the pole core over the pole shoe. In that the coils are winded. So here the four poles are available. These two pole is the N pole. These two are S pole. So the direction of windings are given such a way that it will produce N pole. This will produce S pole, this will produce N pole and this will produce S pole. Right. So this field windings are available in the pole core over the pole shoe. So while the excitation is given, it becomes the magnet. It's called a electromagnet. So the stationary part is the field winding. It will produce the magnetic flux when the excitation is given. The poles are alternatively, N pole and S poles are available alternatively. Right. Now center what we have is the armature. What are the parts available? This is the armature core. Armature core means the place to put the windings is called a armature core. So this dots is nothing but a armature winding. So this is a cross sectional view. Normally it is available in a cylindrical form. This armature core, this armature is available in a cylindrical form. Right. So this is a cross sectional view. So here the armature core is available, over that armature windings are placed. So this dotted line refers the armature winding, so rotating part. In order to supply the current or taking the current from the armature, what we have, the brush is available. That this is nothing but a brushes. This center portion is nothing but a commutator. This commutator is a device to supply the or take the current from the armature. Right. It is a copper coils. This lines, this small line is nothing but the insulation between each and every segment. Right. So what we have here, the brush is available. that will use to collect or supply the current. Then this is the shaft, center portion is the shaft, and this is the commutator, right? So what we have, the commutator available at the center with the brushes in order to collect the current or supply the current to the armature, right? So we have stationary part, in that coils are available. When excitation, it becomes the electromagnet. At the center, the armature conductors available, and commutator with the brushes also available, right? So what will happen if it is motor or generator? We'll see that. So if it is motor, what we are, the mechanical energy is the, motor means electrical energy is the input, mechanical energy is the output. So the electrical energy is given to this armature. So the current is flowing through this armature. So it becomes a current carrying conductor. So in a motor, the electrical energy is the input, the mechanical energy is the output. So the supply is given to this armature. So the current is flowing through the armature coil. So it becomes a current carrying coil. Then excitation is given to this field winding, either self excited or separately excited. The topic is separately available. So excitation means to make this field winding into magnet. Now the supply is given to the armature coil, so it becomes a current carrying coil, and field windings are become a magnet. So what will happen if a current carrying conductor placed in a magnetic field, it experiences a force. Experience a force means it will start rotate. So that is a motor. Electrical energy is given, current is flowing through the armature coil. So this current carrying coil placed in the magnetic field, so that it experiences a force, it will start rotate, right? So this is the magnetic field, is a current carrying coil. In case of generator, what is the input? Mechanical energy is the input. That is, we are going to rotate this armature. While rotating, it should produce the electrical energy. So the generator, mechanical energy is the input and electrical energy is the output. What is the mechanical energy? We are rotating this armature by using either another DC motor or prime mover. Prime mover means diesel generator or diesel engine or petrol engine. By using that, this armature is rotated. Now this field windings are excited. It is a magnet. It becomes a magnet. So what will happen in this generator? When a conductor cuts the magnetic field, an EMF is induced in the conductor. So this conductor is now rotating. Mechanical energy is given, rotating. This conductor is rotating in a magnetic field. Whenever the conductor cuts the magnetic field, then EMF is induced in the winding, in the coil. So that EMF is collected through the brushes. Through these brushes, the EMF, the generated voltage is collected, right? So in generator, mechanical energy is given, it start rotating. At that time, the fields are, magnetic field is available. So when a conductor cuts the magnetic field and EMF is induced, that EMF is taken from through this commutator, right? So this is the machine applicable for both motor as well as generator. Based on the input, it will act as either motor or generator, DC motor or DC generator, right? So the base, it is available at the bottom, the base is available. So it will hold the entire portion of the stationary part as well as rotating part. Now we'll go to the description of this one by one. First we will see the yoke or frame. So that is the thing, outermost part of the machine. So it will hold the entire part. So it is made up of cast iron for small machines and cast steel and silicon steel for large machines. So it's the outer cover that will hold the entire part. So it is made up of cast iron in case of small machine, or cast steel or silicon steel in case of large machine. What is the function of this yoke or frame? Act as a protecting cover for the machine. So it will hold all the all the material, all the windings, everything, and also to give the protection. It is fully covered. Poles are fixed to the yoke, so it serves as a mechanical support for the part. The poles are available. right, the winding. In order to put the winding, the poles are available. During the construction itself, they will decide the pole. Either it is a 4 pole or 6 pole or 8 pole or 16 pole. Accordingly, the construction is given. Over the pole, we can place the winding. So, it is the function is to hold the winding also. Carries magnetic flux produced by the part. So, the poles available, when the winding is given, during excitation the flux is produced. So, this yoke also carries the magnetic flux. It is part of the flux also produced by, carried by the this yoke. It is a function of this yoke or frame. Next, we will go to the pole core and pole shoe. That is nothing but a field poles. Right. The field pole consists of pole core and pole shoe. First, we will see pole core. So, the pole core may be a solid structure or made of laminations. So, this is the place to place the windings. This is called a pole core. It may be solid structure, but normally it is based on lamination. Like a thin sheets, like a notebook, that the sheets are available. Every sheet is laminated so that we can reduce the losses. So that it is given by lamination. Lamination reduces the eddy current loss. It is made up of cast iron or cast steel lamination, right. The solid structure is applicable for only few machines, but normally it is made up of the lamination. Each and every, it is a thin sheet available, n number of thin sheets are compressed together, but each sheet is laminated with the varnish, so that the eddy current loss will be reduced. So, what is the function? The field winding is wound around the pole core. So, the winding is placed in the core. Core means, pole core means, there is nothing but the place to put the windings, right. So, it will carry the field winding. Then pole shoe. The pole shoe is made up of cast iron or cast steel. What is the function of this pole shoe? Support the field winding. Spread the flux in the air gap. Due to larger cross section area, they reduce the reluctance of the magnetic path. So, it is a place to put the winding. So, it will spread the fluxes in the air gap and also reduce the reluctance of a magnetic path. Now, we will go to the next part. Pole coils are field windings. Now, we discuss pole core and pole shoe. So, these windings are placed in the pole core or pole shoe. So, it is nothing but it is a copper wire wound on a former and placed over the pole. I already discussed, pole is the place to put the windings, right. So, this copper wire is the winded and placed in the pole. The field windings are concealed in series with each other. All the field windings are connected together in opposite direction, so that it will produce N pole and S pole alternatively. It is not connected in a unique direction, unique connection. It is an opposite connection, so that the alternate poles are created. They wound in such a direction around the pole core, so that alternate N and S poles are formed, right. So, the connections are given such a way that it will produce N and S poles alternatively, right. So, the pole core and pole shoe we discuss. In that pole core and pole shoe, we are placing the field winding. What is the function of this field winding? When a current passes through this coil, they magnetize the pole, which produce the required magnetic flux. So, the magnetic flux is produced in the field winding. When the excitation is given, it will produce the magnetic flux, right. Then we will go to the rotating part, armature core. So far what we discuss is the stationary part. So, in the armature core, it is a cylindrical shape. I already informed, cylindrical shape. In the diagram what we seen is a cross sectional and is mounted on the shaft. It is a rotating part. So, it is mounted on the shaft. It is a cylindrical shape. It is made of circular stamping, that is lamination. It is not a single piece, it is a lamination. N number of sheets are available. Each and every sheet is laminated and compressed together. It is made up of silicon steel insulated from each other. So, each and every sheet is insulated, so that we can reduce the losses. The laminated structure reduce the eddy current loss. Eddy current loss we'll see later. So it will reduce the eddy current loss. It has slots on the outer periphery to house the armature winding. The slots called a pole. The slots will be there. Over the slot the armature winding can be placed. It is made of silicon steel to reduce hysteresis losses. Right? So in order to reduce the hysteresis losses, it is made up of silicon steel. So what is the function of this armature core? To have armature winding, to place the armature winding, to rotate the armature winding in the magnetic field, produce very low reluctance path, right? So this armature core is a place to put the armature winding and thereby rotating the armature also. Now we will go to the next topic. Now we will see the armature winding. So we discussed armature. In that armature this winding is placed. That is, it is a copper wire wound on a former and placed in the slot. So copper wire is placed in that slot so that it acts as a conductor. So in this winding there are two types available, lap winding and wave winding. There are two types are available. We will see this one by one. So in this lap winding, the number of parallel path equal to number of pole, that is A equal to P. What is number of parallel path? There are n number of poles available mean n number of parallel path will be there. 4 poles available mean 4 paths will be available. The number of brushes is required to the number of poles. Used for high current, low voltage applications. Normally used for generator of capacity more than 500 amperes. Now we will see what is this winding, how it is connected. So this is a coil. These coils are available. This is nothing but a commutator. There are n number of segments are available. So in this lap winding, the number of poles equal to number of parallel paths. So 4 poles available, 4 paths will be available. See this first coil is start from here and it is connected to the second segment. First coil starts here. S1 is starts and go with the finishing F1. It is a start and finish. S1 means start, the first starting. F is the first finishing. So it starts at the coil starts at the first slot of the commutator and finish at the second slot of the commutator. The second coil start from second slot of the commutator and then finish at the third slot of the commutator. So like that the windings are placed. So there are n number of windings are available. Number of parallel path equal to number of poles. Like that it is going, lap winding, right? So each and every coil is closed, right? Start, end, like that it will go. Start from 1, end with 2. Start with 2 and end with 3. Like that it will go. Start in one slot, finish in the second slot. Similarly, start in the second slot, finish in the third slot. Like that it will go. We have the one more winding, wave winding. So another type of winding is wave winding. Here number of parallel path equal to 2, irrespective of the number of poles. So only 2 parallel paths are available, right? Start from one point, it will complete all the poles. Number of brushes is always required is only 2. Only 2 brushes are required. Start, end, like that. Used for low current, high voltage applications. Preferred for generator of capacity less than 500 amperes. So the previous one, lap winding, used for more than 500 amperes. This one used for less than 500 amperes. Now we will see the connection. In wave winding, one end part of coil is allied to the beginning of end part of another coil. So in the previous method, each and every coil having starting and ending. But here, one end of the one coil is the beginning of the another coil. So the same, only one path, only 2 paths available. So we start with one coil, it goes to the beginning of the next coil, has the similar polarity like the first coil. These coils are allied in a wave form and it is called as wave winding. Like a wave it will go, So that it is called a wave winding. We'll see the diagram so that you're able to understand easily. So this is the commutator segments 1, 2, 3. See here, the coil 1 start at the first segment. It will go like this. It will keep on, it is rotate, keep on, it is placed, and end with the, after some places it is end with the finishing S1. Right. So if it is n number of, if 5 poles are available, 5 times it will go and end with 1 point. So starting and ending is S1 and F1 is like a wave, it will goes. But in previous case, each and every coil is completed. Right, start and end with the next slot immediately. Start 1 means it will end with the second slot immediately. Start with the second slot means end with the third slot immediately in the previous case. But here you start here, if 6 poles are available mean 6 times it will go like a wave and finish at the another point. Right. In previous case, 1 pole is completed entirely, then only it will go to the second pole, then third pole. But here all 6 poles are completed in a one like a wave, then it will complete. Right. So that's called a wave winding. Right. I think you were able to understand. Lap winding means each and every pole is completed, then it will go to the next pole. Here all poles are covered by the coil. Right. So these are segments. Now we'll go to the next one, commutator. How this commutator collect the current or supply the current to the armature winding. A commutator converts alternating voltage into direct voltage. It is cylindrical structure. It is built of segments made of hard drawn copper. The segments are separated from each other by microstrip. Is separated by microstrip. These segments are connected to the winding. Right. So we already discussed that. See this diagram. So this is the segment. N number of segments are available. So it's made up of copper and is separated by the mica strip. So there is no connection between these two segments. Right. Segments are made up of copper separated by the microstrip. So it will use to convert alternating to direct current, and one more diagram is available. So I already told it's a cylindrical form. Right. So this is nothing but commutator segment with hard drawn copper to reduce wear and tear. So this is nothing but a copper segments. So these lines is nothing but a mica insulation. Each and every segments are insulated by the mica. There is no connection, there is no short circuit. Right. So that the coil, if suppose if 12 poles are available, mean there will be 12 segments will be available. Each and every pole is supply is given separately from the segment. Right. And also it is insulated by the mica insulation. Now we'll see what is the function of this commutator. The commutator function is collect the current from the armature winding, convert the alternating current into unidirectional current. It produces unidirectional torque in the motor. Right. So it will collect the current, also supply the current. In case of motor, it will supply the current. In case of generator, it will collect the current and also convert into unidirectional current. Right. So the commutator is the important part to collect or supply the current to the armature. Now we'll see the another next topic, brush gear. To collect the current from the commutator and give it to the load. So the brushes are available, copper brushes. Right. The brush gear consists of brushes and brush holder. Because it's rotating part, the brush is available, so it will continuously collect the current from the commutator, that is from the copper segment. So what is brush? The brush are stationary and rest on the surface of the commutator. It is made up of copper, graphite or carbon because it is continuously rotating. So wear and tear will be available. So it is made up of either copper, graphite or carbon. What is brush holder? The brush holder hold the position by means of the brushes are hold in position by means of brush holders. These brushes are held by these brush holders, right? So the commutator is the place to supply the current or take the current from the armature. That is done through these brushes. The current is taken or given by the brushes. So finally what we have, the shaft. So all rotating parts are mounted on the shaft, that is armature winding, brush, everything are mounted. So it is a rotating part. So in this video we discuss about the construction of a machine, DC machine. That is the same machine used as either generator or motor. Accordingly, what are the parts available we discussed, stationary part and this rotating part. Subscribe this channel for more videos. The material is available in the link. The link is given in the description box. The other topics of the DC machine available in the also available in the description box. Thank you. Welcome viewers. In this video we will see the principle of operation of a DC generator. Subscribe the channel for more electrical videos. The link is available in the description box. Soft copy of this material is available in the drive. The link is given in the description box. Now we will go to the topic. So the principle of operation of a DC generator, it is working on the principle of Faraday's law of electromagnetic induction, based on the Faraday's law. The Faraday's law states that whenever a conductor cuts the magnetic lines of force, an EMF is induced. So the conductor will cut the magnetic lines of force, then EMF will be generated. So we need to see what is the conductor and how the magnetic field is produced. The conductor is nothing but a armature. The armature is the rotating part, in that the conductor available. The magnetic field is produced by the field winding, stationary part, so that EMF is generated. When the armature rotates in the magnetic field, EMF is generated. The detailed diagram available at that time, you are able to understand easily. The direction of the induced EMF is given by Fleming's right hand rule. Fleming's right hand rule will give the direction of induced EMF. Fleming's left hand rule give the motor based on the DC motor. For generator, it is applicable by Fleming's right hand rule. Now we'll see the operation one by one. When DC supply is given to the field winding, the magnetic poles will get magnetized and produce the flux. That flux passes through the north pole to south pole through the air gap. So the first step, we are giving the DC supply excitation to the field winding, so that these magnetic poles are magnetized and it will produce the flux that is passing from south pole to north pole through the air gap. So stationary part, field winding, the field windings are magnetized. Now the rotating part, the armature is rotated by means of prime mover in the magnetic field, because generator is a mechanical energy, is the input. There is a rotation that is given by the prime mover. So by using prime mover, the armature is rotated, mechanical energy is given, so that the armature conductor cut the flux. The flux already produced by field winding is cut by this armature conductor. Therefore the flux linking the conductor changes and EMF is induced in the armature winding. Then EMF is according to the Faraday's law of electromagnetic induction. Right? The armature is rotated, already magnetic field is available. So this armature conductor cut the magnetic flux. Due to rate of change of flux, EMF is induced based on the Faraday's law of electromagnetic induction. The EMF induced in the armature is alternating. By the use of commutator, the alternating voltage is converted into direct voltage. The direct voltage is taken to the electrical circuit through the brushes. I will see the diagram, at the time you are able to understand. So the commutator used to collect the current, also convert into direct current, right? It is collected through the brushes. Now we will see the operation. The essential part of generator is conductor and magnetic field. The conductor is nothing but armature, rotating part. Magnetic field available as a stationary part, or field winding. So based on that we can go for the operation. When the conductor move in the magnetic field, it cuts the magnetic lines of force and EMF is induced. This conductor nothing but armature. When the armature is rotating in a magnetic field, it cuts the flux, it cuts the magnetic lines of force and EMF is induced. For understanding purpose, let us consider a single turn of rectangular coil ABCDA placed in the magnetic field produced by permanent magnet or electromagnet. Right? For understanding purpose, we consider rectangular coil with ABCDA with a single turn. Normally it is a circular form, but for understanding purpose we consider rectangular coil. The coil side AB, is connected to the slip ring S1 and CD is connected to the slip ring S2. AB is connected to S1, CD is connected to S2. The brushes B1 collect the current from AB through S1 and give to the external load circuit ML, right? So AB is connected to the brush S1, connected to the slip ring S1. The brush B1 is collecting the current and is giving to the external load of ML. So AB, S1, brush is B1 and the load circuit is ML. Similarly, brush B2 collect from CD through the S2 slip ring and giving the external circuit ML. The coil is rotated in anti-clockwise direction in the magnetic field. As the coil takes different position in the magnetic field, the flux linking and also changes, hence the magnitude of EMF also changes. So we are rotating the coil so that different position will be available. So due to the different position, the fluxes are changes, rate of change of flux also there, so that the EMF also changes. So the brush B1 is connected to terminal M and brush B2 is connected to the terminal L, right? So here, so the brush B1 collect the current from AB through the slip ring S1 and give it to the external circuit ML. Similarly, CD through the S2 and connect to the load circuit ML. Now we'll go to the detailed diagram. So first we will consider the position 1, that is 0 degree. We will go to the entire circle 0 degree, 90, 180, 270, again 0 degree. 4 positions available. So we start with the 0 degree, right? Position 1 at the 0 degree. Now we consider the rectangular coil for understanding purpose. A, B, C, D, A, rectangular coil. So this is nothing but a magnet, either permanent magnet or electromagnet. This is called a field windings. These two are field winding. One is N pole and another one is S pole. So it is named as A, B, C and D. Right? So here we have the two slip ring S1 and S2. The brush B1 collect the current from slip ring S1. Brush B2 collect the current from S2. So the 4 position available 1, 2, 3, 4. The position 1 is the 0 degree, right? It is vertically available. The rectangular is vertically available. Position 2 90 degree. Position 3 again 180 degree, again vertical. Position 4 270 degree, right? So let us assume that this rectangular coil is placed vertically so that the space covered between N and N pole will be very less, right? If it is placed horizontally, so the entire space is occupied by this rectangular coil. Now if it is placed in the vertical, means only less amount of space will be covered by the rectangular coil, right? So due to that, what will happen? The flux coming from N pole is easily passed to the S pole, right? The fluxes are moving from N pole to S pole easily. The area covered by the coil is very less. So what is another term? Rate of change of flux is very less. All the fluxes from N pole easily goes to the S pole, right? There is no rate of change of flux. But based on the Faraday's law, the important thing is the EMF is induced when there is a rate of change of flux. But in this position, due to the coil is placed in a vertical manner, all the fluxes from N pole is linked with the S pole. The rate of change of flux is very less. So the EMF induced also very less in this position. Now we'll see the description. When the coil is at position 1, flux linking the coil is maximum. That is, the flux from N pole is easily linked with the S pole, because the area occupied by the coil is very less, but the rate of change of flux is very less. That is, d pi by dt is minimum. The flux linkage is maximum, but the rate of change of flux is minimum. d pi by dt is minimum. So at position 1, the flux linkage is maximum, but rate of change of flux d pi by dt is minimum. So that EMF is purely based on d pi by dt. d pi by dt is minimum, so EMF also minimum. That is almost 0. At position 0, the EMF induced is 0. Right? Now we will go to the next position. So the second position is 90 degree. The coil is rotated anti-clockwise by 90 degree. So that, see this, it is horizontally available. The coil is horizontally placed. So the area covered by the coil is more. In between N and S pole, the almost the area is covered by this coil. In previous case, it is placed in a vertical manner, so that the area covered is less. So the flux linking from N coil to S coil is very minimum. That is, rate of change of flux is maximum. Right? Because the EMF induced purely based on rate of change of flux. So the flux from N pole is not easily linked with the S pole. The rate of change of flux is more, because the area is covered by this coil. Right? So that is given. The coil is rotated in anti-clockwise by an angle 90 degree, so that it is placed in a horizontal manner. In this position, the flux linking the coil is minimum, but rate of change of flux is maximum. Right? Only the few flux will link, but the rate of change of flux will be more. Right? So based on that, flux linkage is minimum, but rate of change of flux is maximum. So the EMF is based on the rate of change of flux, so the EMF also maximum. Right? At 0 degree, the flux is 0. At 90 degree, the flux is maximum. So in between 0 to 90 degree, it is slowly increasing from 0 and reaches the maximum value at 90 degree. Right? So in this position, the current flows downward in the conductor AB and current flows upward in the conductor CD. Now we will go to the third position. So third position, 180 degree. Again the coil is rotated by anti-clockwise direction by 90 degree. So that again it will come in a vertical manner, but the directions are different, A, B, C, D. Earlier in position 1, the A, B, C, D like this. Here the A is available, now the A is rotated to this position. So it is very similar to the position 1, but only the current direction is different. Right? So the area covered is very less, vertical. It is placed in a vertical. So many areas are available. So the flux from N pole is easily linked with the S pole. So the rate of change of flux is minimum. If the rate of change of flux is minimum, means the EMF induced also minimum, it is almost 0. So in the previous position, the EMF induced is maximum, here minimum. So in between this 90 degree to 180 degree, it is decreasing from maximum to 0. Right? So the details are given. The coil is rotated again by an angle 90 degree. The flux linkage is maximum, but rate of change of flux is minimum, so that the EMF induced also minimum. Right? So it is decreasing from maximum to minimum in this position. From second position to third position, the EMF induced is decreasing from maximum to minimum. Now we will go to the fourth position. So in the fourth position, again it is rotated anti-clockwise by 90 degree. So again the coil is placed in a horizontal manner, very similar to the second position, but the direction is different, A, B, C, D. Earlier A, B, C, D like this, now it is rotated. So again in this position, the flux linkage is very less. So the rate of change of flux is more. The flux not easily link from N pole to S pole because area is covered by the coil, so that the rate of change of flux is maximum. Is given here. In this position, flux linkage of the coil is minimum, but the rate of change of flux is maximum, so that EMF induced also maximum. So in the previous case, EMF induced is 0, now it is maximum, right? So it means that from 0 it is slowly increasing and reaches the maximum value. Now we will see the further details. The direction of induced EMF is given by Fleming's right hand rule. The current flows downward in the conductor CD and upward in the conductor AB. So that is clearly given in the diagram. The direction of current is DCLMBA, right? Now we will see the diagram so that you can easily understand. So this is the induced EMF. So positions are given 1, 2, 3, 4, again 1. So in the position 1, the EMF induced is 0. In position 2, maximum. So in between 1 and 2, it is slowly increasing. So while rotating the coil from 0 degree to 90 degree, the EMF also increases. At 90 degree, it is maximum. Again, while moving from 90 degree to 180 degree, it is decreasing from maximum to 0 and reaches the 0 value at this 180 degree. Again, it is rotating in a reverse direction. From 180 to 270, it is 0 to maximum. From position 4 to position 1, again it is decreasing. It reaches the 0 value, right? So it keep on changes 0, maximum, then 0, again maximum and 0. But the current direction is reverse because the conductors are moving in anti-clockwise direction. So the current will flow A to B or B to A, upward or downward, accordingly it will change. But here we are discussing the DC generator. This is the alternating current, AC. So that AC can be converted into DC, unidirectional DC, like this 1, 2, 3, 4. So that is done by, so the alternating output is converted to unidirectional output or DC output by replacing the slip ring. Slip ring means it keep on changing the position, right? The current will flow A to B, after that the current will flow B to A, slip. It is the meaning, slip is keep on changes. But while using the commutator segments or split ring, right? This is the output is replacing the slip ring by commutator segment or a split ring. Split ring means when the conductor position changes, it will change, it will not change the direction, right? So always it will flow like this in a unidirectional. So by using the split ring, we can convert the alternating current into direct current, right? So in this video, we discussed the operation of a DC generator, how the EMFs are induced. So from 0 degree, 90 degree, 180 degree, 270 degree, again 0 degree. 0 degree minimum, 90 degree maximum. That means slowly increasing from 0 to maximum, 90 degree. 180 degree again minimum, decreasing from maximum to minimum. Again in 270 degree it is maximum, right? It is slowly increasing. So that same thing repeats, right? Subscribe this channel for more videos. The soft copy available in the drive, link is given in the description box. There are other video links also available in the description box. Thank you. Welcome viewers. In this video, we will see the generated EMF, that is the EMF equation of a DC generator. Subscribe this channel for more electrical videos and notification. The soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, EMF equation of a generator. First we'll see the what are the parameters available. The pi is the flux per pole. The unit is Weber. Flux per pole. The Z is nothing but total number of armature conductors. So that is nothing but number of slots into number of conductors per slot, right? So this number of conductor per slot multiplied by number of conductors will give the total conductors in a armature conductor. P is the number of generator poles. So during the manufacturing itself, this number of poles will be decided. A is the number of parallel path available in the armature. This parallel path depends upon the winding, either wave winding or lap winding. Based on that, we can decide the number of parallel path. N is the armature rotation in revolution per minute, RPS. The speed of the DC generator is given by N, armature rotation, that is the unit is revolution per minute. So the E is the EMF induced in any parallel path in a armature. So the EMF is given for a parallel path in a armature. So these are all the various notations available. Now we'll go to the EMF generation. So the generated EMF equal to EMF generated in any one of the parallel path. So now we consider the parallel path first. The EMF generated in parallel path. The average EMF generated per conductor is nothing but d pi by dt. The average generated is d pi by rate of change of flux. There we consider n equal to 1. Normally it is n d pi by dt. Here we consider n equal to 1. So d pi by dt. Now we'll find what is the value of d pi and what is the value of dt. What is the flux available, rate of change of flux, and what is the time taken. So that if you find these two parameters, we can easily identify the EMF generated, average EMF generated. Now flux cut per conductor in one revolution. So there is a rate of change of flux, then only the EMF will be induced. So what is the flux cut? Flux rate of change of flux is d pi equal to pi into p. The flux available and number of poles available in the generator. So pi into p will give the how much of flux cut per conductor in one revolution. So that it is pi into p Weber. The number of revolution per second equal to n divided by 60. This n is the number of revolution per minute. In order to convert into second, it is divided by 60. So the time taken for one revolution is dt equal to 60 divided by n seconds. So the number of time taken is 60 by n. So within a one revolution there are 60 by n seconds. It will take the time of 60 by n seconds. Now we got the value of d pi as well as dt. So d pi by dt will give the generated EMF. So according to the Faraday's law of electromagnetic induction, EMF generated per conductor equal to d pi by dt. The d pi what we calculated is pi into p, flux into pole, divided by the time taken 60 by n. So this n will go to the numerator. So pi p n divided by 60 voltage. So the generated EMF equal to pi p n divided by 60 voltage. So this EMF depends upon what is the flux available in the generator, number of poles, then speed of the generator divided by 60. Now we'll go to the parallel path. So this is for EMF generated per conductor. Now we'll go for EMF generated per path. That is based on the winding, type of winding, either wave winding or lap winding. Now we'll see this one by one. First consider a simplex wave winding generator. The winding type is wave winding. So in case of wave winding, the number of parallel path equal to 2. Always for wave winding, the number of parallel path will be 2. So that number of conductor in one path is Z divided by 2. That is connected in series. So only two parallel paths available. So number of conductor in a path is Z divided by 2. So EMF generated per path is nothing but pi Pn divided by 60 into Z by 2. So earlier we calculated EMF generated per conductor. Suppose if you want to find EMF generated per path means, so this value is the EMF generated per conductor. Within that we are multiplying the number of conductor in one path. So pi p n divided by 60 into Z by 2. So that it is nothing but pi n p pi Z p n divided by 120 voltage. This is for a wave winded generator. Pi Z p n divided by 120. Now we'll go to the lap winding. In case of lap winding, the number of parallel path equal to number of poles. Number of parallel path equal to p. How many poles are available, that much number of parallel path will be available. So the number of conductor in series in one path is Z by p. In previous case we taken Z by 2. Now it is Z by p. The number of parallel path is equal to number of poles. So that EMF generated per path is pi p N divided by 60 into Z by P. Right. So this is the EMF generated per conductor. So this is the EMF generated per path by multiplying number of conductors. Right. So this the P got cancelled, number of poles got cancelled. So pi Z N divided by 60 voltage. So this expression is applicable for wave lap winding. Right. So in general, either lap winding or wave winding, generally one equation is available. Eg equal to pi N Z divided by 60 into P by A voltage. Right. So here this P, the A, number of path. In case of simplex wave winding, A equal to 2. We can substitute A equal to 2, always it is 2. In case of lap winding, A is nothing but number of poles. So that A equal to 2 for wave winding, A equal to P, number of poles in case of wave winding, in case of lap winding. So we can use this. This is the general equation for EMF generated for both lap winding or wave winding. Accordingly, we can substitute the number of parallel path. So pi N Z divided by 60 into P by A voltage. So this is a general equation. It is applicable for both wave winding as well as lap winding. Then we'll go with the angular velocity. The same, the EMF generated EMF is expressed in terms of a angular velocity. For that, this 2 pi is multiplied and divided. So already we have this N by 60 is already available, pi Z P by A is available. So in order to get the angular velocity omega, omega is nothing but 2 pi N divided by 60. In order to bring this order, we are multiply by 2 pi and divide by 2 pi, so that the originality will not change. So the remaining terms are as it is available, pi Z P by A all are available. So this 2 pi N can be replaced by omega, that is nothing but angular velocity. 2 pi N divided by 60 is nothing but a angular velocity. Then remaining terms are available, this 2 pi available, this pi Z P by A. So this equation is also the generated EMF in a DC generator. It is given in terms of velocity. In a problem, or if while solving the problem, if a angular velocity is available, we can use this formula, omega pi Z divided by 2 pi into P by A. Right. So this is the general equation for either lap winding or wave winding. We can use this. So this equation applicable when the angular velocity is given. So in this video, we discuss the generated EMF of a DC generator for both lap winding as well as wave winding, and also one more expression for including the angular velocity. So subscribe this channel for more videos related to the electrical topic, and soft copy of this material is available in the drive. The drive link is given in the description box. Thank you. Welcome viewers. In this video, we will see the types of a DC generator. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. So the types of the DC generator. So based on the excitation of DC generator are classified as follows. The classification is based on the excitation given to the DC generator. Excitation means the supply given to the field winding in order to make it as a magnetic field. So in that there are two types available, separately excited or self-excited. So primarily two types. The excitation is given separately to the field winding in order to make it to as a magnet flux, in order to produce the flux, or self-excited. These field windings are connected with the armature. So by self itself it will produce the magnet by using the concept called residual magnetism. Right. So based on the excitation, the generators are classified. The major classification is separately excited or self-excited. Excited means giving the supply to the field winding in order to make the magnetic field, so that produce the flux. So that we have separately excited, separate DC supply is given to the field winding for excitation. Here the field winding is connected in series with the armature, So the self itself, it will produce the magnetism, right. So the separately excited, self-excited. The self-excited, again it is classified into three different type. That is the armature winding and field winding, how it is connected. So it is connected in series, mean it is series generated, armature winding and field winding. If it is connected in parallel, means shunt generated. Both it is both having shunt winding as well as series winding, means it is compound generator, right? The field winding is connected series here, field winding is connected in parallel here. Here both connected in series as well as parallel. So that is called a compound winding, combination of both series and parallel. This compound generator, again it is classified into two different type. Long shunt compound generator, short shunt compound generator. Short shunt means the shunt winding is connected immediately to the armature, thereby series winding is connected. Long shunt generator means the series winding is connected immediately to the armature. The entire circuit is connected in series with the shunt winding, shunt field. So that is called a long shunt or short shunt. The detailed diagram is available at the time, we are able to understand easily. Right. So in this short shunt and long shunt, we have the series field winding as well as shunt field winding. Two windings are available in both the type. So due to the two winding, again it is classified into two different type, cumulative compound or differential compound. If series winding and field windings are added together, then it is called a cumulative compound. If it is opposing each other, then it is called a differential compound. That is applicable for this type also, short shunt compound generator, right? So this is the classification. We will see this classification, we will see the types one by one. So first we will see the separately excited DC generator. The generator where field winding is excited or energized by external DC source is called a separately excited DC generator. The excitation is given separately. Now we will see the diagram. So this is the armature winding, rotating part, armature winding. This is the field winding, stationary part, right? So the generator, so it will generate the power, the energy that is available in the load end. So for this field winding, it is given, the excitation given separately by the another DC source through this rheostat. In order to control the voltage applied to the field winding, this rheostat is used, right? So the DC supply is given while adjusting the rheostat. This winding become, field winding become, current will flow, then magnetic field will be created, right? So this excitation is given separately. This is the field winding, this is the armature winding, right? So due to this interaction between this armature and field winding, the EMF is generated. EMF is generated in the armature. So that is available at the load terminal, right? So this is the field winding RF, is the field current, rheostat and DC source. This RA is the armature resistor. Current flowing from the armature is the armature current, IA. While going to the load end, it is IL. Right. So this EG is the EMF generated inside the armature, but while going to the load terminal, some drops will be there. So that is nothing but this, the armature resistance drop, IARA, and as well as load voltage, right? The EMF generated from that, this armature resistance drop is subtracted, the balance will be available at the load end, right? So these details are given here. So the IL is the load current, IA is the armature current, IF is the field current, RA armature resistance, IF RF field resistance, EG generated EMF. Now we will see the equations. So the output power is nothing but V into IL, the load voltage and load current, V into IL. So in this case, this IA and IL both are equal. The current from the armature is equal to load current, both are equal. So by applying the KVL, the EG, this is the voltage rise, this is voltage drop. So the EG is nothing but IA minus EG minus IARA minus V equal to 0, or otherwise the generated voltage E equal to the voltage available at the load terminal plus the armature resistive drop IA into RA, right? So the generated EMF is the sum of the voltage will be dropped across IARA, the remaining available at the load terminal. So the sum of these two is nothing but generated EMF, Eg equal to V plus IA RA. So there is small drop in the armature circuit, that is called IA RA. So the power developed in the armature is Eg into IA, generated EMF into IA. But while going to the load end, it is V into IL. Some voltage will be dropped here, so some of the power will be reduced. The balance power available at the load end, right? So this is inside the armature. This is outside the armature, that is the load terminal. Eg into IA is, while going to load end, it is V into IL, right? So there is a small drop called IA and RA. Right? Now we'll go to the second type. So self-excited DC generator. So previous one separately, the separately excitation given. Now it is self-excited, that is a DC generator where field windings are excited by the current supplied by the generator itself, are called as self-excited DC generator, right? The current from the field winding, the generator where the field windings are excited from the generator, the current supplied by the generator itself is called a self-excited. There is no external circuit is required. How it is possible? This is due to the property residual magnetism. What is residual magnetism? Where some flux is always present in the pole of the machine. Even after the removal of the supply, some of the flux will be always available in the winding. That is called a residual magnetism. Now we will see the residual magnetism in detail. The property of the magnetic material to retain the magnetic property even after the removal of magnetizing current is called a residual magnetism, right? So after removing the supply, some of the flux will be there, some of the magnetic force is available, that is called a residual magnetism, right? In such machine, the field windings are interconnected with the armature winding, right? The field winding and armature windings are interconnected. The field coil may be either in series or in parallel, or both in series as well as parallel with the armature winding, right? So this armature and fields are connected in a three different way, either in series or parallel or both series as well as parallel, right? So that due to residual magnetism, the field windings are become the magnet, and also this armature winding field winding is connected. So the current generated from the armature is passing through the field winding also. So based on that, it is classified as shunt generator if it is connected in parallel, field winding and armature winding. Series generator, both field winding and armature windings are connected in series. This compound generator, both connected in series as well as parallel. Now we will see these types one by one. So in the shunt generator, the generator in which the field winding is connected in parallel with the armature winding. If field winding and armature windings are connected in parallel, then it is called a shunt generator. Now we will see the diagram. So this is the armature, rotating part. So this is nothing but a brush. This is a field winding. Now both are connected in parallel, right? So the current generated from the armature is used to excite the field winding also. So that it is called a self-excited. Now this is the load end. Armature as well as field are connected in parallel. So that called a shunt generator. Now we'll see this. So the generator EMF will be generated inside the armature. It's called Eg. This RA is nothing but a armature resistance. So the EMF generated, so the sum of the value will be dropped across this armature resistor in the RE. The balance will drop across, balance will go to the voltage, the load terminal voltage, and also some of the voltage will drop across this shunt field winding also, right? Now we'll see the term. So this is the EMF generated inside the armature, armature resistance. Then we have this IA. So here the IA will come. So that IA will be splitted, ISH and IL, load current and shunt field current. So based on that, we will see the equation. The output power is nothing but V into IL. terminal voltage into load current. But what is the power generated in the armature? Eg into Ia. Eg into Ia is the power generated in the armature. After the drop, the balance will be available in the load terminal, right? So it is very, you need to clearly, we need to explain. The voltage V is the voltage available in the load terminal. Eg is the voltage generated in the armature, right? So both are not equal. This Eg, there is some drop will be there, balance will be available as a load terminal voltage, right? So that we'll see this equation. Here Ia equal to IL plus ISH. The armature current flowing from the armature is splitted into ISH and IL. So ISH, the current flowing through the shunt field winding, is nothing but V divided by RSH, because the voltage across this RSH is nothing but voltage across the load terminal. Both all are connected in parallel, right? So what is the equation, the KVL? Eg minus IaRa minus V equal to 0. So this is the voltage rise. These two are voltage drop. Or otherwise bring these two term in the left hand side, so that right hand side, so that Eg equal to V plus IaRa. The EMF generated inside the armature is equal to the terminal voltage plus the drop Ia into Ra, right? So that these two are not equal. Sum of the voltage is dropped across the armature. Balance is available as a load terminal, right? So this is a very important equation. Eg equal to V plus Ia Ra. Generated voltage equal to terminal voltage plus the resistive drop, armature resistance drop, Ia Ra. I will see the further detail. So Ia equal to IL plus ISH. So for effective power to the load current IL should be very high. Right? If the load current IL is very high, means the power will be more. So that ISH should be very small. The current diverted through the shunt field winding should be lesser, so that IL will be more. So the ISH is made to high resistance, so that less amount of current will flow. The high resistance mean it is made up of many turns of thin wire, so many turns available, so that only less amount of current will flow through the shunt field winding. That is, the shunt field winding, the current is very less, so that the resistance were increased. So it is made up of many turns, right? So if ISH is very small, mean the IL will be more. If IL will be more, mean more power will be delivered to the load circuit. Now we'll go to the second type. Second type is the series generator. Series generator means the field winding is connected in series with the armature winding. Field winding and armature windings are connected in series. Now we'll see the diagram. So this is the armature winding, rotating part. This is a field winding, stationary part. Both are connected in series. In previous type it is connected parallel. Now it is connected in series. So what will happen here? The current flowing from the field winding, the current flowing from the armature winding, Ia is equal to ISH, current flowing through the series field winding, and also it is equal to the load current. So the only one current is available. This armature current flowing through the series winding, load current, all are equal. That is given here. Ia equal to ISH that is equal to IL, right? So this generated EMF is Eg, right? The generated EMF will be Eg, so that some of the voltage will be dropped across armature resistance and also dropped across series field resistance. Balance will be available at the load terminal. So that is very important. The voltage generated inside the armature Eg, after the balance, after the drop across armature resistance and series field resistance, balance will be available at the load terminal, right? So that is given here. EgIa equal to EgIsc plus Eg into IL. All are same because current is equal. What is the equation, voltage equation? Eg minus IaRa minus Isc Rsc minus V equal to 0. So this is a voltage rise, voltage generated. These are all drops. Drop across armature resistance, drop across the series field resistance, drop across the load terminal. So it can be written as Eg equal to V plus IaRa plus Isc into Rac. That is Eg equal to V plus Ia into Ra plus Rac, right? Because Ia equal to Isc. So the generated voltage is equal to terminal voltage plus drop across the armature as well as the field. Right? Some of the voltage will be dropped, balance will be available as the load terminal, available at the load terminal. Right? So the remaining term is the output power if you consider V into IL, the terminal voltage into load current. Right? Now we'll see the further detail. Since the series winding carries full load current, the value of RSE should be less. RSE is designed with a few turns of thick wire. Right? The RSE, because if the RSE is lesser, then only the full amount of current will flow. Right? If the RSE is very large, means the current will lesser. But here all are connected in series, so we need to increase the current flowing through armature as well as field winding as well as load, so that RSE should be lesser. Right? So RSE is designed as lesser, so that very few turns available with a thick wire. In previous case it is opposite. So many turns are available with a thick wire. RSE is more, right? Because it is diverted, it is connected in parallel. Now it is connected in series. We need to increase the current so that RSE is kept to very minimum value, so that very few turns with thick wire is available. Now we'll go to the third type. The third type is a compound generator. That is, it is a generator in which few turns of field windings are connected in series, few turns of winding is connected in parallel with the armature winding. So both series as well as shunt, series as well as parallel is connected. The field windings are connected series as well as parallel, both are available. So that is called a compound generator. In the first type only shunt winding connected in parallel. In second type only connected in series. In the third type both connected in series as well as parallel. So based on that it is two type, long shunt and short shunt. Right? The shunt winding is available after the series. Here short shunt means the short winding is available immediately, after that series winding will be available. We will see the diagram so that you are able to understand. So due to the two winding, again it is classified into cumulative compound or and differential compound. Whether the two windings are added together means cumulative compound. Two windings are opposing each other means differential compound. Now we will see the diagram. What is cumulative compound and differential compound? See, this is the two windings. This is a series field and shunt field. The compound generator, we have both series winding as well as shunt winding. Is connected in series as well as parallel. See the current direction, both are equal. The current enters here and leaves here. Here also current enters here, leaves here. Right? So that the magnetic pole, magnetic flux will be same in both the series winding as well as parallel winding. So it is a cumulative, both will be added together. That is given here. If the flux produced in the series field winding and shunt field winding tends to aid or support each other, it is said to be a cumulative compound generator. Right? So because of same current direction, both the flux will be added together. So that is called a cumulative compound. In case of differential compound, see the current direction, current enters in the top coil, but here current enters in the bottom coil. So both the current directions are opposite to each other. So for example, here N pole created means here S pole will be created. So both will oppose each other. So that is called a differential compound generator. The current directions are not equal, both are opposite to each other. That is, if the flux produced in the series field winding and shunt field winding tends to oppose each other, then it is said to be a differential compound generator. Right? Here current directions are opposite and flux also opposite, so that called a differential compound generator. Now we will go to the long shunt and short shunt. So long shunt compound generator means the generator in which the shunt field winding is connected in parallel across the series combination of series field winding as well as armature winding. Right? The shunt winding is connected across these two windings, so that is called a long shunt. We will see the diagram, so it is easier to understand. So this armature winding is available, immediately the series winding is connected. Across these two field winding is connected, shunt field winding is connected, so that it is a long shunt. The series winding is coming immediately, shunt winding is coming afterwards, so that is called a long shunt. right? This long shunt mean the shunt winding is connected across the combination of series winding as well as armature winding, right? Now we'll see the diagram. So this is the generated EMF, EG. This is the load terminal voltage. So after the drop, the balance voltage will be available at the load terminal. What are the drops available? This RA, armature resistance, armature resistive drop. Then this shunt, then series field is available, and shunt field also available, right? So what about the current? Here IA, the current coming out of the armature winding is IA, while flowing through the series circuit is ISC. So both are equal, IA and ISC are equal. Armature current as well as series field current are equal. So at this point it is splitted, load current and shunt field current, ISH and IL, right? So IA equal to ISC, that is equal to sum of IL plus ISH, right? So we'll see the drop, what are the drops available. So the output power will be V into IL, load terminal voltage and load current, right? So the power generated inside the armature is EG into IA. After the drop, the balance will be available here. So what are the drops here? IA equal to ISC. The armature current and series field current is equal. Similarly, IA equal to IL plus ISH. IA is split into load current into ISH. So ISH can be written as V divided by RSH, because RSH is connected across the load terminal, right? So that the same voltage will be applied across RSH also. So the current through the shunt field winding is V divided by RSH. Right. Now we'll see the voltage equation. So EG minus IARA minus ISC RSC minus V equal to 0. Right. So this is the generated EMF. That is converted into sum of the voltage is dropped across armature resistance, sum of the voltage drop across series field winding, sum of the voltage drop across the load terminal, or otherwise you can write it as EG equal to V plus IARA plus IARSC, right? So the terminal voltage, the generated voltage equal to terminal voltage after this drop. The balance, after the drop, balance voltage is V, right? So it can be written as IA, because this ISC both are, this ISC is equal to IA, so that we can write IA into RA plus RSC. So the generated voltage is dropped across the load terminal after this drop across armature as well as series field resistance. Now we'll go to the short shunt. Short shunt generator. See here, this is the armature rotating part. Immediately the field winding is connected, so that is called a short shunt. After that only series winding is connected, right? Immediately the shunt field winding is connected, so that is called a short shunt. After this only the series field winding is connected, so that is called a short shunt, right? So what are the terminal, what are the parameters available? This EG is the generated voltage, V is the voltage available at the load terminal. After the drop, the remaining voltage will be available at the load terminal. So this RA is the armature resistance. This IA is the current flowing from the armature. At this point, what will happen? Both will be splitted into ISH and ISC, shunt field current and series field current. This armature current is splitted into the shunt field current and series field current. This series field current is equal to load current also. Both are connected in series. So ISC equal to IL, right? Now what are the drops available here? We'll see this diagram. EG minus IA RA minus ISC RSC minus V equal to 0, right? The generated voltage from that armature resistance drop is subtracted, series field resistance is subtracted, then load voltage, that is equal to 0, or otherwise EG equal to V plus IARA plus ISC RSC. The generated voltage is not fully available as a load terminal. Some of the voltage will be dropped across the armature resistance, some of the voltage will drop across the series field resistance. This after this drop, remaining will be available as a load terminal, right? So the other terms are output power equal to V into IL. power generated inside is Eg into Ia. So we already discussed Ia equal to Is plus Ish is splitted, but Isc equal to IL, right? So Ia equal to IL plus Ish. So the Ish can be calculated as Vsh divided by Rsh, right? So the remaining voltage after the drop, the remaining voltage available at the load terminal. So coming under short shunt generator. So in this video we discuss about the various types of DC generator, that is separately excited, self excited, again shunt generator, series generator, compound generator. Again it is split into short shunt, long shunt, then further classification differential compound and cumulative compound, right? So subscribe this channel for more videos. The link is available in the description box. The material link also available in the description box. Thank you.